Alright guys, we are starting Unit 2, Section 1, which is all about periodic properties and trends. So at this point you are not going to be doing guided notes, so you need to write these down in your notebook. You also should have a periodic table out in front of you this entire time. The first slide of this notes was done in class. It was the metals, nonmetals, and metalloids properties. So if you didn't get that, make sure you get that from somebody else. But you can write this section of notes right after the metals, nonmetals, metalloids properties. Alright guys, so we're going to do a little bit of review first from Unit 1. So we're going to start off with how the periodic table is organized. So if you look on your periodic table, you'll notice that it looks like it's organized by atomic mass, or average atomic mass, but it's not. If you look at some of them closely, some of them don't follow in line with that trend. But what is always true is that the atomic number is increasing by 1 all the way over the periodic table. The other thing that we learned last unit was about what our groups are and what our periods are. So the groups are the vertical columns 1 through 18, and your periods are the horizontal rows 1 through 7. And where the element falls on the periodic table, specifically which column it is in, that is where we can see different trends developing. So the first thing we're going to talk about is nuclear charge. And nuclear charge is related to the number of protons in the nucleus. And remember that protons are positive, and that positive things are attracted to negative things. So we're going to be dealing with that concept this whole unit. Positive things attracted to negative things. What happens if one charge is bigger than the other? So, as the number of protons inside the nucleus of the atom increases, the nuclear charge increases. So, let's say we have chlorine versus, or let's do carbon versus lithium. So, lithium has 3 protons because it has an atomic number of 3, and carbon has 6 protons. So that means that lithium has a nuclear charge of +3 and carbon has a nuclear charge of +6. Because carbon has more protons, it's going to attract negative things more. It's going to attract negative things better. In this case, our negative things that it's attracting are the valence electrons. We're going to be talking about the valence electrons this whole time. So, as you move across a period, nuclear charge is going to increase because we keep adding more protons from left to right. Then we have this thing called shielding. So shielding is exactly what it sounds like. Shielding, it's a block, it's a wall. It blocks the attraction from the valence electrons to the nucleus. And what happens here is we have energy levels, and inside these energy levels we have electrons. So I'm going to draw a little picture here before you kind of do some writing. So let's do lithium. So lithium has a positive nucleus, and it has 2 energy levels with 2 electrons in energy level number 1, 1 electron in energy level number 2. So we already know that the valence electron is attracted to the nucleus. They want to be close together. But we also know that 2 negative things repel each other. Oh wow, we have some negative things in between. So this electron and this electron are repelling our valence electron. So they're acting as a shield. They are blocking the attraction from the valence electron to the nucleus. So the more energy levels you have, the more interior electrons you have, and those interior electrons are what are blocking the attraction from the nucleus to the valence electrons. So if that attraction is lowered, then it's easier for electrons to leave an atom because there's not as much holding it onto the atom. So our shielding trend is on here in dark blue. So across the period, shielding is constant. It doesn't change. So you can see that with this guy here. Shielding is constant. It is not changing, and that's because we have the same number of energy levels and the same number of shielding electrons all across the period. But down a group, this way, each time we go down a group, here's 1, 2, 3, 4, 5, 6, 7, we get more energy levels, where francium right here has 7 energy levels and hydrogen here only has 1. More energy levels means more interior electrons. More interior electrons means there's more things to block the attraction from the nucleus to the valence electrons. So, this is going to play out in a couple of ways. We're going to be thinking about how, cool, attraction is increasing this way because we're adding protons, but our valence electrons are staying constant. But going down a group this way, we have more protons. Yay! We should have more, that's more nuclear charge, but we also have more energy levels. So that means we have more shielding. So from left to right, there's more attraction, but down, not so much, because we got those extra energy levels kind of blocking the attraction, canceling out that extra proton stuff going on. So here's why that matters. Atomic radius, the size of the actual atom itself, okay, the radius, that number there, R, the radius is affected by that attraction between the nucleus and the electrons. If there's more attraction, then the protons in the nucleus will pull the valence electrons in tight. So if I have a big positive nucleus, it's going to pull the electrons in really close. If I have a little positive nucleus, the electrons are going to be more spread out because they're not as attracted to the nucleus itself. So let's relate that back to what we know about nuclear charge and shielding. So if all of this has to do with the attraction, let's think about what makes an electron more attracted to the nucleus. Okay, well, the negative thing will be attracted to more positive stuff. So if there's more protons, if there's an increase in protons, that's going to increase the electrons. If there's not very many energy levels to reduce that charge or to reduce that attraction, then that's going to be a very attractive nucleus. If there's a lot of energy levels, again, we're going to block the attraction to the nucleus. So our largest atoms are going to be the ones with a lot of energy levels, and they're going to be the ones with the fewest protons. Our smallest atoms are going to be the ones with the most protons and the fewest energy levels. So our trend here has francium being the smallest and fluorine being the smallest and francium being the largest. So here's that trend again. In this one, they took out the D block elements, the transition metals, just to kind of simplify it a little bit. So going from left to right, atomic radius gets smaller. Again, because we are increasing the number of protons, or the nuclear charge, and that makes the attraction larger. And across the period, these all have the same number of energy levels, so that means they have the same amount of shielding. Down a group, however, you have, get out of here, I'm just going to delete all that. Down a group, however, remember we have more protons, so that's exciting, but we also have more energy levels. So each time we add an energy level, we're increasing shielding and we're decreasing the attraction. Less attraction means larger atom. So all of our other trends, we've got two more, fall back to that effective nuclear charge, that nuclear charge and shielding combo. So ionization energy is a new one, and ionization energy is the energy required to remove one electron from its neutral state. So that means I have an atom here. We'll do lithium again. Okay, 1, 2, boom. And I'm going to remove this electron. How much energy did that take? That's what ionization energy is, because we are creating an ion. Specifically, we're creating a cation because we are removing an electron. So in general, ionization energy increases as you move across the period from left to right. And this is, again, because of that attraction. I know you're sensing a common theme here. Wow, Miss Nyman keeps saying attraction over and over and over again. Yeah, it's really that important. So ionization energy increases as you move across the periodic table. So what that means is that if there is a large attraction from the electrons to the nucleus, it's going to be really hard to tear off an electron out of that atom. So I like to think about this with, dating and relationships. It's easiest that way. So this is really awful advice that I'm giving you. Don't actually take this advice or do anything that I'm about to say. But it will be helpful to kind of understand what's happening. So let's say you have a friend, and your friend has a girlfriend, sure, and the girlfriend is the electron. And you're rolling in there, and you want to take that girlfriend, and you want to make her your girlfriend or best friend with her consent. So you are coming in, and you want to know how much energy is it going to take for you to separate her from her boyfriend, to remove her from that relationship. In this case, it depends on how good their relationship is. Are they very strongly attracted to each other? Have they been dating for a long time? Do they have a good relationship? Do they fight a lot? Whatever. If they're awesome together, they're the best couple in the whole wide world, they're Cinderella and Prince Charming, whatever, it's going to take a ton of energy on your part in order to remove her from that relationship. Now, if they're constantly fighting and if they hate each other and they're bitter rivals secretly, but they feel obligated to stay together, then it's going to be really easy for you to go up in there and break up that relationship. Now, don't do any of these things because that's not a very good friend thing to do, and also we don't really need to be dating in high school because it makes a hot mess and it's just not what we need to do. Focus on you, focus on your education, you be you. Woohoo! Here is what our ionization energy trend kind of looks like. Notice that it's not a perfect trend. It's not going to just completely increase this way and decrease this way. That would be nice. That's what we're going to assume. We're going to pretend like it does for this class, but it's not perfect. None of this is ever exact. Okay, the last trend we're going to talk about is electronegativity, which is the ability of an atom in a compound to attract electrons from other atoms. So let's say I have chlorine and I have hydrogen, and they have a bond, and that bond is 2 electrons that they're kind of sharing. Okay, now chlorine is way better at holding on to electrons than hydrogen is. Hydrogen is really bad at it, and we'll explain why in a second. But what's going to happen, instead of them being equally shared like this, I'm going to figure out how to erase finally on my iPad. No, that's not how you do it. I gave up and just had to delete it. So instead of chlorine and hydrogen holding the electrons equally, what's going to happen is the electrons are going to be more attracted to chlorine. So they're going to be way over here at chlorine, even though they're still being kind of shared with hydrogen. So chlorine is going to be an electron hog. So here's the reason why that occurs. Remember that chlorine is on the far right side of the periodic table. Chlorine has a lot of protons, meaning it has a high nuclear charge. It has only a few energy levels, so it doesn't have very much shielding. And therefore what's going to happen is chlorine has a ton of attraction to the nucleus. Hydrogen only has one measly little proton. Sure, it doesn't have a lot of shielding, but it's only got one little baby proton. So hydrogen isn't going to be able to hold on to the electrons as much because the electrons aren't going to be as attracted to the hydrogen nucleus as they are to the chlorine nucleus. When we're talking about the trend going from top to bottom, so from left to right, electronegativity increases. And then from bottom to top, it also increases. And that again is due to the attraction. Remember, way down here, they have tons of energy levels. More energy levels, more shielding, less attraction. So they're not going to be as good at holding on to their electrons. They're not going to be able to go and get electrons from anybody else if they can barely hold on to their own. So there's a lot of vocab in this unit so far. We've got a ton of vocab. I'm going to pass back your vocab sheets next class so you can start practicing. But even start with Quizlets, start with flashcards, do something. But don't just wait until the last minute to try and cram all this vocab into your brain because it's not going to end well. And this is a really short unit. So make sure that you start studying, start quizzing yourself, make a study guide for yourself, whatever you want to do, start doing it now instead of waiting longer.